So, welcome everybody. This is going to be chapter 16 of chemical structure and reactivity. I'm your host, Palladium, and on the bottom we have our shoutout list, both from Discord and YouTube. If you want to be added to the shoutout list, you can DM me or ping me in Lectureland. I'd be happy to add you to a growing list. So, let's get straight into it. So, this chapter won't be as hard as the other chapters, such as chapter 5, which was on molecular orbital theory, or the organic chemistry chapters. I especially did not like reading those chapters, but reading this one was definitely a relief. So, instead of going on about organic chemistry, we'll talk about some inorganic chemistry. And we're specifically going to look at main group chemistry, which is going to encompass both groups 1 and 2 of the periodic table and groups 12 to 18. So to start off with that, we will look at some basic reactions in different types of compounds. And then we will also look at some specific compounds that engage in such reactions such as dimerization or polymerization. And finally, we will talk about various groups and periodic trends. To your left right there, that's going to be an image of hexanitrogen. Now, hexanitrogen is simply an allotrope of nitrogen that has 6 nitrogen atoms attached, and it has use in energy storage, as those bonds contain a lot of energy in them. So, before I get into this, let's take a quick look at the periodic table. So I grabbed this diagram directly from the book, and you can see we're going to cover groups 1 and 2. Group 1 is commonly known as the alkali metals, and group 2 is known as the alkaline earth metals. And these are essentially going to be metals that you usually find in ionic compounds. And that's because they give up their valence electrons really easily. Now, for any of y'all that have looked at the periodic table lately, you might see there's group 12 here. However, group 12 appears to be in the D block, which is where all the transition metals are. But we're only covering main group chemistry, which is pretty much anything but the transition metals. So why do we have something right in the transition metal block? Why do we have group 12 there? Well, the exact reason is because its valence electrons are in the s orbital, and that s orbital is going to be filled as you go once we get to group 12. And so those are actually not going to count as transition metals. And in fact, they react more like the main group elements. So we just place them there regardless. And for those who don't know the term main group elements, representative elements is also a good way to talk about it. It's the same term, essentially. And you can see group 13 to 18, instead of metals, although there are a few, you're primarily going to see a lot more non-metals here. So for example, group 18 will be your noble gases, group 17 will be halogens, and these are non-metals, don't get me wrong. But if you look at something like group 14, right? Lead is in this group, and lead is very much a metal, and a toxic one too. So let's talk more about the properties of these groups. So I already went over groups 1 and 2 and group 12, but I also wanted to talk about trends as we go across these groups. So say for example, we start at group 1, we go across to group 18. According to this image I pulled directly from the textbook, we see that we get a gradual transition from metals such as lithium and cesium all the way to non-metals such as argon and fluorine. And in fact, you can see there are elements that are sort of in between. Another way to call them, they're called metalloids here in the US. But since it's a British textbook, they call them semi-metals and semiconductors, so it's different. Same principle though. So for compounds such as silicon, they're semiconductors that have some properties of metals, but also some properties of nonmetals. Now, If you remember me talking about oxidation states back in chapter 1, you remember that essentially it's just a way to describe the quote unquote, I'd say, charge on an atom. And as we move across the groups, we get a greater tendency for an oxidation state of group number minus 12. So what do I mean when I say this? So take, for example, group 15. So group 15 is 15 minus 12. We're going to have a greater tendency for a plus 3 oxidation state as we move along group 15. Now, we do know that these elements, they can form compounds. Think water, your polymers, and in addition, they can also form these compounds in different crystal arrangements too. Now, when we talk about compounds, we have to say whether they are stable or unstable. And if you open up any piece of chemistry literature, you will find something talking about the stability of a compound. Now, there is no one fashion in which a compound can be stable or unstable. So, for example, phosphorus pentabromide, that's going to be unstable as it decomposes over 35 degrees Celsius. 35 degrees Celsius is, I'd say, like 100 something Fahrenheit for us Americans. But you can see that it does get unstable after that. However, for phosphorus pentachloride, it does not decompose over this temperature, and so we don't consider it unstable. Now, there are other compounds such as nitric oxide, which some piece of literature might call unstable. However, they can just simply be reactive with other compounds. So nitric oxide, it can interact with oxygen molecules in the air and, well, it's not unstable, it just reacts with other compounds. And the same goes for diatomic sulfur. Diatomic sulfur, S2, that exists at temperatures above 720 degrees Celsius. But below it, what happens is that it polymerizes to form sulfur rings. And on that topic of sulfur, you can see the image chart left here. So generally, when you see sulfur as like a normal stinky solid at room temperature, it exists in primarily two forms, orthorhombic or orthorhombic and monoclinic. Now, they both have 8-membered rings, or so these rings have 8 sulfur atoms. However, these rings themselves, they don't change. The only thing that changes is the actual packing. And so that's how we can figure, hey, how exactly do these rings pack? Anyways, going on about stability, I want to talk to you about the difference between a thermodynamic and kinetic stability. So, when we look at the stability of a compound, thermodynamic quantities give us a great insight into how stable said compound is. And specifically, the standard change in Gibbs free energy can tell us how stable it is. So, for example, imagine the reaction with sulfur trioxide with water. The standard change in Gibbs free energy is going to be negative 71 kilojoules per mole. Now, if you do remember basic general chemistry, a negative change in Gibbs free energy, whether it's standard or just Gibbs free energy, tells us that a reaction is spontaneous. And in addition, if you look at the relation between Gibbs free energy and the equilibrium constant, if Gibbs free energy change is negative, the equilibrium constant will be, well, it'll become higher. And so we're going to get a desirable shift towards the products in a reaction. And in fact, this negative value for Gibbs free energy tells us that the product, which is sulfuric acid, is preferred in equilibrium. Now, let's take another example of a reaction where the standard change in Gibbs free energy is also negative. For example, the decomposition of hydrazine. Now, as a fun fact, hydrazine is actually pretty useful in rocket fuel. So with the European Space Agency, what they have is the Ariane series of rockets. And as fuel, these rockets use hydrazine and various derivatives of hydrazines for launch and rocket fuel, as the compound is pretty energetic. But anyways, although the Gibbs free energy at standard conditions is negative for this reaction, and hydrazine is thermodynamically unstable if we only care about that change, it is kinetically stable. And that's because there's an energy barrier that prevents this decomposition in practice. And so, although if you look at the overall picture of a reaction and you calculate the Gibbs free energy change, a compound may appear unstable, kinetically it very much can be stable in regards to kinetics. So the next type of reaction I want to talk about, going on about stability, is called disproportionation. And excuse my pronunciation for that. But going on, certain compounds are unstable, and because of their instability, they can decompose according to disproportionation reactions. Now, what are those exactly? Well, these reactions happen when you have some sort of compound. Like take, for example, aluminium to fluoride. What's going to happen is that's going to decompose into aluminium and also aluminium fluoride. And so this aluminium at the reactant, they'll have a +2 oxidation state. Of course, solid pure aluminium will have an oxidation state of 0, but this particular compound, aluminium fluoride, aluminium will have an oxidation state of +3. And so you can see there are reactions where you're going to have a product that comes from a reactant that is both reduced and oxidized, meaning that we get one species where the oxidation state is reduced and one where the oxidation state is, well, increased. And to be specific, this kind of reaction is a specific case of a redox reaction where electrons are transferred. Now, you may be wondering, why exactly do these reactions happen? And well, these reactions simply happen because if you have one oxidation state of an ion, it's going to be higher in energy compared to its higher and lower oxidation states. So we're going to get two compounds that have a higher and lower oxidation state, respectively. Now, going on even more about high oxidation states, if we look at main group chemistry, or if we look at the representative elements, it is shown that compounds that have the highest oxidation states have fluorides and oxide ions. Now, going on with that example of sulfur hexafluoride, that is a very known gas, and if you've seen anybody inhale that on like a talk show or on live TV, it makes your voice really deep. But sulfur hexafluoride, the thing about it is it has sulfur in an oxidation state of +6. And this phenomenon where we get really high oxidation states is typically because, especially for fluorides, that's because the fluorine-fluorine bond is very weak due to pi antibonding orbital occupation. And for those who don't understand pi antibonding orbitals, here it is shown on the right. And essentially, these are orbitals in, if you fill it with electrons, any potential pi bonds are going to be broken, or any potential constructive overlap between p orbitals. Now, in addition to pi antibonding orbital occupation, bonds to fluorine are also very strong because fluorine is highly electronegative. And in addition, fluorine is small compared to the other halogens. Now, when you look at the decomposition of a sulfur halide, not specifically sulfur hexafluoride, it could just be any halide. it's more obvious that it's thermodynamically favorable if the halide was, well, chlorine instead of something such as fluorine. And that's because the chlorine-chlorine bond, that's going to be stronger than the bond between two fluorines in the diatomic fluorine molecule. Going on about compounds being stable or unstable, I want to talk about hypervalent compounds. Now, if you look at the image to my left, you can see that we have some carbon with 5 bonds coming out of this. You don't want to do this in your organic chemistry class if you're taking it. This is known as a Texas carbon, and it's called Texas carbon because it forms that little star. And the reason why you don't want to do that in your organic chemistry class is because it breaks a very simple rule, known as the octet rule, which is where an atom needs 8 electrons in its valence shell to be stable. But with 5 bonds, carbon's going to have 10 electrons, which exceeds 8, of course. However, there are very much compounds, such as sulfur hexafluoride, that break this octet rule. If you look at that structure of it, sulfur has 6 bonds coming out of it. That's 12 whole electrons. So, that can be possible for atoms such as sulfur and phosphorus. They can form these hypervalent compounds. And going on about molecular orbital theory, what's going to happen is if we look at hypervalent compounds for our second period elements, such as nitrogen and carbon, if we look at methane, right, CH4, all those electrons, 8 electrons, they'll go into bonding molecular orbitals, which will make the molecule more stable. But for something like NH5, those 8 electrons will go into bonding molecular orbitals and 2 in non-bonding orbitals, which actually makes it a bit weaker compared to something like methane. Now, going on more about the molecular orbitals of hypervalent compounds, it is obvious that as we go down from the second period to the third period, more atomic orbitals will be available. And therefore, once we get to compounds such as sulfur and atoms such as sulfur and phosphorus, we have more atomic orbitals available. And in addition, we have the 3D orbital available. And in fact, what this orbital specifically does is it can make non-bonding molecular orbitals slightly bonding, improving the stability of their hypervalent compounds. And in fact, this is shown in the image to the right here. So this image shows surface plots of the molecular orbitals of sulfur hexafluoride. And in principle, these should contain some sort of contribution from the 3D atomic orbital. And you can see that, well, it's obvious that certain atomic orbitals from 3D create contributions here. And in addition, the fluorine 2p atomic orbitals also contribute to bonding. Now, what if instead of just rationalizing the bonding of hypervalent compounds using something like a d orbital, why not use the hybridization thing I was talking about back in chapter 5? So, for those who don't know where the idea of hybridization came up in this book, imagine a molecule such as methane. Methane is essentially carbon bonded to 4 hydrogens, and that carbon is going to have tetrahedral geometry around it. However, carbon's valence orbitals are going to be 2s, which is just a sphere, and 2p. 2p consists of 3 different orbitals, 2px, 2py, and 2pz. And all of these orbitals are going to be at perfect right angles to each other, or in other words, 90 degrees. However, for a molecule such as methane, we're going to get an angle of 109.5 degrees, which cannot be explained simply by looking at 90-degree angles. So therefore, we came up with hybridization, such as sp3, sp2, and sp. sp3 corresponds to a tetrahedral geometry with 4 hybrid orbitals. sp2 corresponds to a trigonal planar with 3 hybrid orbitals. And sp simply creates a linear geometry with 2 orbitals. However, with the introduction of d orbitals, could we also come up with sp3d and sp3d2 orbitals? Yes, we can. And these two new types of hybrid orbitals correspond to trigonal bipyramidal, which is going to be right here, and an octahedral geometry. And you can see octahedral molecular geometry, that's going to be present in sulfur hexafluoride. Now, hypervalent compounds are only feasible for elements that are from third period and below. And that's simply because, well, you can't form them from second period elements. Their bonding gets progressively weaker. And so for third period elements, these hybrid orbitals are only made of the 3s, 3p, and 3d orbitals. Now, we know that there are 2s and 2p orbitals, so why doesn't the 3d orbital interact with 2s and 2p? Well, the reason for that is because all of the 3s, 3p, and 3d orbitals are the closest in energy together, meaning that it's going to be feasible for them to hybridize. Anyways, going on about hybrid atomic orbitals, we have to be careful when we're talking about them. And that's because we don't want to say that molecules such as sulfur hexafluoride, right? We don't want to say that they simply exist because 3d orbitals form the hybrid atomic orbitals. Instead, what we want to say is that hybridization is the only rational explanation that we have for describing bonding using normal 2-electron, 2-center bonds. And 2-electron, 2-center bonds, that's essentially just going to be your normal bond between two different atoms, pretty much. Now, here's the kicker. There's actually not that much evidence to demonstrate that the 3d orbitals are actually involved in bonding within sulfur hexafluoride. The only reason why we use hybrid atomic orbitals is because it is the most convenient way of describing bonding with these particular bonds. Alright, so I think I have talked enough for now. If any of you guys want to send any questions in Lectureland, don't send them in this chat. Send them here. Send them in Lectureland. I'll make sure to answer them. Alright, no questions. I can keep going on. Alright, no problem. Now, I have talked all about this time about how to describe bonding in hypervalent compounds using d orbitals. However, what if we don't use d orbitals? And in fact, what we can use instead are symmetry orbitals, which we discussed initially in chapter 5. So take for example this compound, phosphorus pentachloride. Essentially, we have a phosphorus atom in the middle. We're going to have 3 equatorial chlorines and 2 axial chlorines. And instead of using d orbitals for phosphorus atom, we can simply use molecular orbitals formed from symmetry orbitals. And using that, we can actually rationalize bonding using molecular orbital theory, as shown in the diagram below. And look, it's our first problem. So what this question is essentially asking is using Vesper, predict the number of bonding and lone pairs in the valence shell of the central atom. And in addition, I want you to determine any suitable hybrid atomic orbitals on the central atom. And tell me if there are any multi-center bonds present. Multi-center just means that you have two electrons pretty much spread out over a bunch of atoms instead of being bonded between two atoms. And to make it a bit easier on y'all, uh, I'll give you just a chance to do part A of this problem. Alright, y'all got like 1 minute. Alright, so going on to the solution, take for example this, interhalogen compound, ClF3. So on this, according to Vesper, we're going to have 3 bonding pairs, as shown in the bonds here, and 2 lone pairs on that central chlorine atom. Now, we can also describe this bonding using sp2 hybrid atomic orbitals. And in fact, we can also describe the chlorine being involved in 3-center 2-electron bond. In other words, another way to reference this 3-center 2-electron bond is known as a banana bond. Now, you can actually see these banana bonds present in compounds such as diborane. And essentially, take for example this molecular orbital right here. We're going to see that pretty much we got electron probability spread out across this hydrogen, this particular boron atom, and this particular boron atom. And so we call certain compounds, such as diborane, which you can't explain using normal 2-center 2-electron bonds, as electron deficient. Because, simply put, if we look here, we have 12 valence electrons. So how many bonds do we have? 1, 2, 3, 4, 5, 6, 7, 8. And so, using our 2-center 2-electron bonds, what we're going to see is we're supposed to have 16 valence electrons. However, we only have 12 valence electrons. So this is going to be an electron deficient compound. And we're also going to have banana bonds here. Going on more about oxidation states as I discussed earlier in the chapter, the most common oxidation states of sulfur are going to be +2, +4, and +6. And the exact reason for this is because electrons are paired up in valence shells. And in addition, molecules such as SF5, what's going to happen with them is you have sulfur and oxidation of +5, but they're free radicals, and therefore they are very reactive. And in fact, you can see there's a dimer of this. Now, for sulfur, you actually can see a case where you have an oxidation state of, +3, and that's going to be in the dithionite ion. And also, just for a quick note, take for example if you have sodium chloride. The oxidation state of that is going to be +1, But in something such as sulfur hexafluoride, the oxidation state is going to be +6. But of course, there are no sulfur ions where you're going to have 6 electrons just taken away. That's not going to happen. Anyways, time to get on to the reaction. So, I want to talk about hydrolysis. And hydrolysis, if you take that very literally, it just means splitting of water. And if you look at a compound such as boron trichloride, if you react that with water, you're gonna get boric acid, and you're also gonna obtain something of some acidity from protons, and also you're gonna get free chloride ions. Anyways, if we look at ionic chloride, which is specifically sodium chloride, just for this case, those ions are going to be separated. And those ions, both cation and the anion, they're going to be covered by polar water molecules. And that's because, well, water is naturally a polar solvent. And so there's going to be a dipole, and that dipole is going to very much interact with the charges of the ions. Now, you can see on the image to the left, we have pretty much an aqueous sodium ion that's surrounded by these polar water molecules. And in fact, what we can observe is that when a water molecule comes closer to that sodium ion is, well, if you put that in organic chemistry terms, electrophilic. And so that ion is going to pull electron density, which will weaken the oxygen-hydrogen bond, but it'll also make that bond more polarized. And in fact, when we have metals coordinated to water, the greater the interaction, or the more strong the interaction is, the more acidity will be present in solution. And that's going to be because as that interaction strengthens, that oxygen-hydrogen bond will weaken. And as it gets weaker, there's greater chance that more protons will become free in solution. And going on about acidity and pH, we can see that the reaction of the water molecules around a cation, they can actually create some acidity in solution. So take, for example, we have this specific complex and we react that with water. What we're going to have is there's going to be a reversible reaction established where on one side we're going to have our normal reactants here, but on the other side we're going to have the hydronium ion, which is acidic. Now, if we look at specifically the sodium ion, the initial species of that aqua complex, it will have a pKa of 14.5. However, if we look at something such as magnesium and aluminium ions instead of sodium ion, because they're going to have a greater charge, there's going to be a greater weakening of the oxygen-hydrogen bond. And so therefore, we're going to get an increase in acidity. Matter of fact, that aluminium water complex is slightly acidic. And because of that, the pKa is going to drop. Now, by changing the pH of these solutions, these products can actually become favored. And so we can get an acidic solution simply by dissolving an ionic chloride in water, which is pretty wild to think about. And in fact, you can see it in this graph I got from Wikipedia. As we change the pH of this beryllium solution, we're going to get different species formed here. Now, going on about how molecules react with water, we can see that there's a difference between boron trifluoride and boron trichloride. And that's simply because the initial reaction between boron trifluoride and water will create an initial adduct. And this adduct, you can see compound A, that can be extracted and it essentially acts as a strong acid. However, when we add an excess of water to these compounds, we can have this reaction, this particular one on the bottom, going over and over again, which later forms the tetrahedral complex, BOH4 minus. And in fact, this tetrahedral complex can be formed by boric acid too, BOH3. And if you put that in water, you're going to get that complex. Now, here's a fun fact. When you heat boric acid, you can actually see them condense together to give metaboric acid. Now, that's enough talk about boron. Let's go on about group 14 halides. So as you can see in the image on the top, chloromethane reacts with water via the SN2 reaction. My chemistry teacher showed this to me back in freshman year, and that's the first way I learned about SN2 reactions. And as you can see, the first step, we're going to get protonated methanol, essentially. And, well, that's going to be highly acidic, of course. Now, when we look at other compounds such as dichloro and trichloromethane, they are also going to react in similar reactions, which are thermodynamically favorable, but they're kinetically slow. And so that leads into that thermodynamic versus kinetic stability concept that I talked about at the start of this slideshow. Anyways, going on about group 14 halide, something such as silicon tetrachloride that can rapidly be hydrolyzed to give SiOH4. Now, as we go to group 15, what we're going to see is for compounds such as phosphorus pentachloride or phosphorus trichloride, once they react with water, they're going to end up forming phosphonic acid and phosphoric acid. And here's a fun fact, phosphoric acid is a compound that is used in Coca-Cola and other various soft drinks. But anyways, going on about more group 15 elements, something such as arsenic can form arsenic acid and also arsenous acid. Now, going on about group 16 chloride, there is no such compound as sulfur tetrachloride, but we have sulfur tetrafluoride, which actually can be hydrolyzed in a similar fashion to the group 15 halides. And in fact, that product that we're going to get, SOH4, that can give up a water molecule and end up forming sulfurous acid. Now, going on about another group 16 element, namely tellurium. That can form orthotelluric acid. And although the name says acid, you would expect it to be acidic, this is actually a hexabasic compound. Now, we're going to be on the topic of oxides too. And there are particular chlorides such as zinc chloride. And if you dissolve that in water, we're going to get a zinc alkyl complex. But as we increase the pH, solid zinc precipitates. Solid zinc hydroxide, that'll precipitate into a gelatinous kind of substance. Now, if we increase the pH even more than that, we're going to get a particular complex again, ZnOH4 minus. And there are also other amphoteric oxides that come from group 13, 14, and 15. This image I took from Wikipedia, but you can see all these grayish, which are actually green, but pretty much grayish oxides, those are shown as amphoteric. So something such as aluminium oxide. Alright, so we've encountered our second problem here, and this is going to consist of two parts. So we're given pKa values of specific hydrated ions in the table below. And in addition, we have to use VESPR to look at what exactly the shape of molecular selenium tetrafluoride will be. And going on to the solution, we can see that as pKa gets higher, acidity will of course decrease. And because of that, the interaction between the metal ion and the oxygen in water, that will become weaker. And as for SEF4, we're going to have one lone pair and four bonding pairs, which will get us a sawhorse structure. Now, hydrolysis can actually be compared to SF4, which gives selenic 5 acid. Anyways, and that's enough talk about chlorides and all that. Let's go on to oxides. And there are three particular types of oxides that I need you to know. Basic oxides, such as sodium oxide. They are formed from electropositive elements, such as alkali metals, as they become cations. And of course, oxygen will form the oxide anion. And they will dissolve in water to form basic hydroxides. However, for something such as acidic oxides, which is like sulfur trioxide, they are going to dissolve in water and they'll form an acidic solution, which in this case is sulfuric acid. Now, there are amphoteric oxides, which are in the middle, as they can act both as a base and acid. So I think we're at the stopping point. We're at an appropriate stopping point to let me answer any questions you guys may have about this chapter so far. Alright, no problem. So, anyways, let's talk about the chemistry of each group. This is going to be the final stretch. So, first off, group 1. Group 1 is known as the alkali metals. And these metals can easily give up their valence electron in their ns orbital. Now, we know all of the group 1 halides, and in fact, most of these halides have the crystal structure of either sodium or cesium chloride. And in addition, these halides have normal property of being soluble, except for lithium fluoride. Now, the oxides of group 1 are all basic oxides, and are in the form M2O, which is, well, pretty normal. Now, going on about properties as you go up and down this group, lithium is the most likely to participate in covalent bonding, which makes sense because back in chapter 11, we directly talked about organolithium compounds in organic reactions. And just for a quick refresher, these organolithium compounds are used to create carbon-carbon bonds. And because of the difference in electronegativities, they're going to end up forming new bonds. And in fact, lithium also has application in, well, energy storage, specifically lithium ion batteries. Anyways, going on to group 2 elements are known as the alkaline earth metals. And beryllium is going to be the odd one out of all these metals. And that's because it is the most likely to form covalent bonds, specifically because it has the lowest energy orbitals. Now, the halides of beryllium are not considered ionic. But if we look at a compound such as beryllium oxide, It's not, it's going to be sort of ionic, but it is actually pretty stable. Now, the halides for the rest of group 2 are all ionic. And specifically for magnesium, its coordination number is going to be 6, while the rest are going to have a coordination number of 8. Now, there are no halides in the form Mx, which in this form, M is going to refer to an alkaline earth metal atom having only one electron removed. That's not going to happen. And that's simply because if we look at Mx versus Mx2, due to Coulomb's law, there's going to be a stronger lattice energy. There's going to be greater electrostatic attraction between the cation and the anion. Now, magnesium is also useful as they're used in Grignard reagents. Grignard reagents work along with organolithium reagents to form carbon-carbon bonds, as we covered back in chapter 11. Going on to group 12, which is going to include zinc, cadmium, and mercury. They all are going to have their valence electrons in their s orbital. And in fact, looking at the energies of the 4s orbital in all elements, there's going to be a slight increase and then a drop. And that's primarily because of relativistic effects. For those who don't know what relativistic effects are, imagine that you pretty much have an electron going around a nucleus of an atom. Now, as the nucleus is going to increase in charge, that electron's going to have to move faster and faster. But we know that mass changes dependent on an object's velocity. And so that's going to create a shrinking in orbitals, and that's going to affect the energies of said orbitals. Now, you only ever see that with heavy elements, though, so no need to worry about it if you're working with the lighter elements. Anyways, about group 12, the halides of group 12 elements are all solids. And as you use heavier halogens, so take for example fluorine to iodine, as you go down that group, more covalent bonding emerges. And in fact, these oxides are amphoteric. Going on about ionic compounds, we can observe that mercury 1 compounds, which just have the mercury 1 ion, are in fact unstable in respect to disproportionation. Now, we already covered Grignard and organolithium reagents, but we can form more organometallic reagents from group 12 elements, either in the form RMX, where X is the halide and R is the rest of the molecule, or MR2. Although zinc and cadmium are unstable in the form of MR2, so I would be careful of that. So finally, we are pretty much out of the metal exclusive groups, and we're going to see in group 13, we're going to have both metals and non-metals in the same group. Although, well, pretty much the only non-metal or metalloid is going to be boron. Now, we already talked about the boron halides already, and we know that they don't dimerize. However, if we look at compounds such as aluminium chloride, they're going to form covalent network solids. And as we go down the group, the oxides, they gradually turn from acidic, so take for example boron oxide, to amphoteric and to basic. And, well, not even the slide nor the book can fully go over the amount of borates, or compounds that simply have boron and hydrogen. There's simply too many of them to count. However, if you are interested in looking at borates, you can actually learn how these atoms are arranged in 3D space using something known as Wade's rules. Now, going on to group 14, this group has carbon, which is, well, the base of all organic chemistry, silicon, germanium, which are two semiconductors, and the only reason why I'm presenting this to you guys right now, and full-on metals with both tin and lead. Now, the halides of silicon and carbon are actually pretty known, but Silicon can form hypervalent ions that can form into acids somehow. Going down the group, the tetrahalides for germanium and tin, they exist as discrete molecules. And these molecules are going to form molecular solids or gases. Now, if we look at the oxides instead of the halides, the oxides of carbon are going to be acidic. Matter of fact, when you try dissolving carbon dioxide in water, you're going to set up a reversible reaction where you have carbonic acid. Now, if we have something such as silicon dioxide, that's not going to be as acidic, and here's a fun fact, it makes up pretty much every rock. Now, the rest of the oxides are amphoteric, and in addition, they get more complex with even crazier oxidation states as we go down group 14. Now, group 15. So this slide's going to be pretty short. So the halides for this group, they're going to show an interesting range of properties. So for nitrogen and arsenic halides, they're going to be gases or molecular solids, and they can all be hydrolyzed by water. However, one commonality with all these halides is that they act as Lewis acids, or electron acceptors. And on a side note, nitrogen and phosphorus can form a wide range of oxides. If you look at the image to the bottom, we have P4O6 and P4O10, which have really interesting and interconnected structures. Anyways, here is our third and final problem. So this one states that nitrogen dioxide reacts with water to form two particular acids. It asks us to give the equation for the reaction and how exactly you would classify this reaction by looking at the oxidation states. Going on to the solution, it is obvious that this gives both nitric and nitrous acid. And this is specifically a disproportionation reaction, as NO2 has an oxidation state of 4, and nitric acid and nitric acid, they have an oxidation state of 5 and 3 respectively. Going on from group 15, group 16 is actually pretty similar when you're going to look at other groups such as group 14 and group 15. As you move down, you're going to get elements that are closer to metals. Now, going on about halides, the only known halide of oxygen is OF2, but sulfur is more versatile in how it forms halides. And that's because sulfur has two well-known, never mind. Going on about sulfur, sulfur also has two well-known oxides, SO2 and SO3, sulfur dioxide and sulfur trioxide. And the other oxides are pretty well known. Now, as you go down group 16, those oxides will become more and more basic. And here's a fun fact, sulfur and tellurium can also form acids, in addition with selenium. So here's pretty much going to be the closing slide. So this is going to cover group 17 and 18. We already talked about the halides enough, but just on a quick note, there exist interhalogen compounds with interesting geometries such as I7 or iodine heptafluoride. And this particular compound has a geometry I can only describe as I think I did forget it, but let me just think for a second. I think it was something like pentagonal bipyramidal. But this is a pretty interesting geometry. Anyways, going on to group 18. This is going to consist of noble gases, which don't react with anything, therefore they're going to be called noble. However, there are some gases that do react, such as argon, as shown in argon fluorohydride, and xenon. And, well, xenon does whatever it wants with fluorine. It forms a bunch of compounds with it. So that's pretty much going to be the end of chapter 16 of chemical structure and reactivity. And going on with more inorganic chemistry, we will be talking about transition metals. And using molecular orbital theory, we're going to discuss coordination complexes and how exactly they form and the effects of different ligands. Now, these coordination complexes can be observed in different ways, whether it's through magnetism, spectroscopy, or thermodynamics. And finally, we will cover more about oxidation states.